So hello everyone, also from my side. My name is Simon Voss. I am the former managing director of eLab of RWTH Aachen in Germany and currently the founder and CEO of Battery. And today I would like to talk to you with Abdellah, Cherkaoui and Kenza Maher about the future of battery technologies. But before we dive into that, I'll look at the presenter. And I would like to introduce both of you briefly and then also hand over the mic to understand a little bit more about your profession and your current projects. So starting with Kenza Maher, she's a scientist at the Qatar Environment and Energy Institute and has a focus on battery materials research. And if I'm informed correctly, you're looking specifically on the thermodynamics and kinetics of battery materials.
Yeah, I'm also developing new materials.
Okay. I think the microphone.
It's here.
Ah, okay.
Yes.
Perfect.
Can you hear me? Yeah.
So, Kenza, would you like to elaborate a little bit more on what your actual or current projects are that you are focusing on? In a couple of words.
Can I get the presentation?
So they will switch the presentation, then you can introduce yourself with a couple of more words and a little bit of information on your research. And afterwards, we will switch over to Abdellah and talk about your current endeavors. So, Kenza, would you like to talk about? I will give you the presenter.
Well, as Simon introduced, I'm a scientist at Energy Center in Kiri, which is Qatar Environmental and Energy Research Institute. I will first talk a little bit about our institute. Then after that, I will elaborate on our work in battery field. Qatar Environmental and Energy Research Institute is part of Hamad bin Khalifa University, which is part of Qatar Foundation. We do have 4 centers: Energy Center, Water Center, Environmental and Sustainability Center, and Corrosion Center. I'm part of Energy Center. Well, those are our activities on especially lithium-ion batteries. We do, because Qatar temperature is very high, especially in summer. You are lucky, for people who are not familiar with the weather in Qatar, you are lucky that still the temperature in Qatar is still low, even though it's May. It's normally, the temperature in Qatar is, in summer is 45 degrees C. That's why for using batteries, which is normal lithium-ion battery that exists in the market, it's suffer a lot from the temperature and the degradation. That's why we do have challenges for lifespan comparing to other countries, and also the battery degradation. High temperature means also the safety concern, where the battery will catch fire and will have thermal runaway. To mitigate these challenges, we are doing our research on stationary and EV application. We are supporting those. Batteries by developing different strategies of testing the thermal runaway and also the heat generation of the existing batteries. We are developing next generation materials, different type of materials for sodium and lithium-ion batteries, and also we used to develop materials for sodium batteries. Also, as everyone knows, there are scarcity of lithium needed materials, which are cobalt, nickel, and also lithium. That's why we start innovation on recycling of the existing lithium-ion battery. We do have facilities and labs where we do material synthesis and processing. We do material fabrication, we do material scale-up, and we do material characterization using our collab for characterization of the materials. We do also do battery engineering where we fabricate the cathode and the anode material electrodes. We also do the battery assembly. We do the material recycling, as I just mentioned. For the battery assembly, we can do small battery cells to big pouch cells. We, as I mentioned, we have to test the battery aging of the batteries, that it's either our traditional batteries or also the developed battery, where we do the battery performance, degradation tests, and this is for battery cell to battery module. We do environmental tests at different temperature, and also we do safety tests at using isotherm calorimeter or accelerate rate calorimeter. We also, as I mentioned, we are doing some real-life tests in grid application and also in EV support. We do have 500 kilowatt battery energy storage system, which is connected to 250 kilowatt power PV systems, where we test and we do the battery integration, and also we do the degradation of those battery during summer and during winter time, and we compare this data. For the EV application, we do have chargers, two types of charger, fast charger and level 2 charger. We compare the change of this charger and the charging time, and also the charging effect on the battery of the EV car. Unfortunately, I did not put here our collaborators, which are Muwasalat. We are also doing with them some tests on their cells on the electric buses. We do have our collaborator also from Ministry of Defense, which also we test their cells that they are using for their application. And we have another collaborator, which is Inventus Power, which is a company that they are producing battery cells, lithium-ion battery cells. And we are also doing some tests with them at different temperature and different C rate to check the effect of the temperature. Thank you so much.
Thank you, Kenza, for introducing. I only need the presenter. Thank you. For introducing your work. And I would like, Abdellah, to talk to you a little bit about, or ask if you can talk about what you currently do. You have many ventures ongoing, and you are senior advisor at Aqualith, for example. So in terms of battery innovation, what is your current focus? If you can elaborate in a couple of words, and then we head on to a detailed discussion about the future of battery technologies as such.
Sure, absolutely. So I am currently co-founder and chief commercialization officer at Aqualith. It's an early stage startup. It's a spin-off from the University of Baltimore in Maryland and the US Army Research Lab with new battery chemistries, new materials, covering the anode, electrolyte, and the cathode. And we are currently working on commercialization, our first generation product, which is 100% silicon anode that is actually quite affordable compared to other. And there are quite a few. It's been looked at for quite a while, and there is quite a bit of promising companies in the field.
Very interesting. I will come back to the silicon anode in a bit. Because I know out of my research how difficult it is to industrialize a silicon anode. But before we dive into the detailed discussion, I would like to give the audience a little understanding of if the presenter works. Go one second back. Give me a second. about the innovation on battery technologies. So to give you a little hands-on experience and visual impression that, yeah, we need to be fast, but we need to be aware that battery technologies, and that is a picture out of our lab at ELAB at RWTH Aachen of the Battery Abuse Center, that batteries are not just some devices, but are very, very delicate and sometimes also dangerous technological inventions. So yes, we need to be fast. I think everyone agrees in order to accelerate innovation for e-mobility, but with deliberation. And to put it in the words of John B. Goodenough, one of the pioneers of battery innovation, batteries are good, but we need to do a lot of work in order to improve them more. The good news here is that the scale up, right, and the industrialization of battery technologies is a safe bet, because batteries are needed everywhere in terms of e-mobility, but also beyond that for stationary storage. If we look at renewable energy generation, to balance the grid, to act as battery buffers, and all of that will compound to a compounded annual growth rate of about 30% per year, leading up to the year 2030. So we are really looking into a bright future if we do it right. And what we are discussing today is, what are we doing in order to realize this outlook that we are having ahead of us? Batteries are quite complex, and I just wanted to put up this chart really quick to give you an understanding of how many points of technological innovations are needed in order to provide a safe, functional, and also high-performing battery in terms of environmental considerations, but also in terms of user perception. And the chart that you see here is the outline of the EU Commission stating all the requirements on battery technologies in the coming 6 to 7 years. So just to give you an understanding, we will monitor the carbon footprint, we will have some CE marking on the cells, we'll have something that is called the battery passport in Europe, and I think this gives you an understanding of what is also required in the future globally in terms of battery requirements. And we jointly work on making all these requirements possible, I hope. So this sounds quite easy, but out of experience I can tell you of our work at ELAB that the scaling from the invention to the market expansion always has to pass the piloting phase. So what do I mean with this? I touched on this yesterday in my keynote. You start with an invention, you have an idea, and then you scale it up, right? You start with the lab equipment, and then at some point you need bigger equipment. You need testing devices, you need computational power. So the investment, the costs are increasing. Yet, as you see, the uncertainty whether the technology will be successful in the end is still there. And so the entrepreneurial uncertainty arises, and that is what creates the innovation barrier. And our goal is, and our task is, to push through this barrier and help companies also to push through it to make it all the way to the market. So I would like to keep this in mind when we now enter our discussion on topics of battery innovation. And yes, that brings me to my first question. And Kenza, I would like to start with you. So the topic is the future of battery innovation. If you look 5 years ahead, what are the key materials? We may come to silicon in a second, but from your perspective, what are the key materials that we need to focus on that allow us to leverage the performance of battery technology?
Well, I can see there are many different types of cathodes and anode materials, either for lithium-ion or for sodium-ion, and also for solid-state batteries that we will need to work on. But I can see that there are people now, either scientists or researchers or even the companies, they are working on two types of to develop the new materials, which are the cost and the performance. Mm-hmm. If you ask me what can I see as technologies coming on in the next 5 years, I can start first of all by a solid-state battery or all solid-state battery, which it's a really big jump. It's a very high risk, but also is very high rewarded. Solid-state battery increase the energy density. Also, it increase the safety of the battery, as you show. What we can see that here, it's in the lab, but if you see it in car, it's a really very dangerous. And also for stationary, is very big batteries. I know that for solid-state batteries, still a lot of things to do, especially when it comes to cost.
Yes.
But there are a lot of innovation, and there are people working on this. Any breakthrough innovation, I can see those batteries is coming in 5 years.
So you have a positive outlook on all solid-state batteries.
If it's not solid state, we can start by some semi-solid. State.
So maybe to elaborate for our audience, semi-solid batteries are, so an all-solid-state battery is a completely rigid component. Currently, we have batteries which have an anode and cathode and a liquid electrolyte in between in order to transfer the lithium ions. Yeah. And then an all-solid-state battery would have a solid electrolyte, which has the ability to prevent fires and thermal propagation when being damaged. Well, and now semi-solid is kind of a transition towards, or from the liquid state to the solid state, having a gel-type electrolyte. And this already combines the benefits of both. So we have a high conductivity, which is still a bottleneck for the performance of all solid-state batteries, but we have the fire protection and the safety of this technology, right?
Totally. I think for 5 years from now, the semi-state batteries will be the more commercialized, because as I mentioned, like this semi-electrolyte, it is providing both the high energy density and also the thermal stability, and also the high ionic conductivity, which is the issue for solid-state batteries.
Yes.
Also, except then that it's still also the cost. Solid-state battery and semi-solid-state battery still costly, but with the innovation in the process, I can see it coming in 5 years.
Okay, interesting.
Also, I can see the sodium-ion batteries.
Yeah, before we touch on that, I would like to hand over the mic to Abdellah really quick to give your perspective on the development, and then we go to the next technology maybe to have a joint discussion on this. So Abdellah, what do you see 5 years ahead? If you give us an outlook and an overview of the different technologies, do you agree with the outlook on all solid-state batteries? What's your perspective?
So let me start with, this is a great graph. Let me start by saying there are several pieces to the commercialization of batteries. And first and foremost, we are here at the autonomous electromobility. So we're talking about electric vehicles. And I should start by saying various battery technologies can be applied to various energy storage, whether mobile or not. It can be your cell phone, consumer electronics, power tools. It can be aerospace. It can be military. It can be electric vehicle. It can be energy storage for the grid. All of those are important. What's interesting is there are several stages here, and you mentioned the increased investment cost as you're moving past the idea, the innovation, the proof of concept, the scaling up, production. And so what's interesting is there are quite a few very promising technologies that actually could already be commercialized in a watch or in a cell phone, which would have, you're going to change your cell phone over a period of 1, 2 years, 3 years, so calendar life, couple of years. Now we're talking energy storage, we're talking about massive scale, massive amounts over 20, 30 years of calendar life, over tens of thousands of cycles of charge and discharge. Now we get into the process.
Very different applicational areas, right? We have very small and short-lived battery technologies on the one end of the spectrum, and on the one end of the spectrum, and on the other end of the spectrum, we have those big batteries, which also account for e-mobility and stationary storage, which have to live long. So you mentioned calendar life, which is the calendaric life, and cycle life. So we have to distinguish between these two requirements, which means we cycle them very, very often, hundreds and thousands of times, right? So to distinguish for the audience between these two
the application.
requirements.
Well, let's go to electric vehicles. Actually, so funny story. I'm trying to remember. So the gentleman from Politecnico University of Milano,
yes,
yesterday, Sergio, showed a really interesting piece, which is an electric vehicle or any vehicle has a calendar life of 10 years or 5 years, depending, it's going to, it has essentially, if it charges and discharges 1,000 times and has a range of 300 miles, that's 300,000 miles. For any of you who owned a vehicle for 10 years, I don't know if you drove 300,000 life. The funny story is when you talk to people who don't have an electric vehicle and you tell them, yes, I'm looking at 1,000 cycles as the maximum cycle life of that battery. I will never drive an electric vehicle unless it has 100,000 times charge and discharge.
Yes. People don't have an estimation of what this really means in terms of kilometers in total of the battery life.
Yes, so the illustration here is the difference between the application and how long it should last and how many times it can charge and discharge.
So coming back to thank you for sorting this out for us. So coming back to the materials question, right? If we consider the application of e-mobility, so speaking about large volume, a lot of tons of battery material needing to be produced, and then also the application requirements in terms of calendaric life and cycle life. Do you see a viable business case for what Kenza mentioned from a technological point of view, you having more the market perspective for all solid-state batteries or even other technologies that you would like to mention here briefly to say like, hey, this will have potential, this will probably likely not have that much potential on the market. So coming from research, leading all the way to the industrialization.
So the initial requirements are performance and cost. Since I've been working on this with Aqualith this past year, I've came to define the cost of performance rather than cost or performance.
Okay, gotcha.
The issue here is we know the requirements. Let's have faster charging. Let's have more energy density at a lower cost. We've seen the cost of the kilowatt hour decrease significantly faster than. However, one of the issues is there are today proven in the lab and even at pretty advanced technological readiness levels for new battery chemistry that have performance, that have some sort of promise of cost, or that have very good performance at a higher cost, or lower performance at a bigger cost. I think we might talk about LFP and NMC in some point. But the key piece is one of those guys that introduced the gigafactory concept, which is to meet the volume necessary to produce at scale the hundreds of thousands of vehicles is really how do you manufacture at scale? And today, really the key question is, once you have proven those new chemistries, how do you get them to that production at volume?
I agree. So we have proven with the gigafactories that you mentioned, and even the overproduction already, especially by the Asian markets or the market participants, that we're able to produce lithium-ion batteries with the current NMC and LFP technology that you mentioned at scale. I think that is a given fact, and everyone agrees on that. So Kenza, having the visionary perspective on the future technology, I'm, from my academic perspective, a little bit hesitant on saying all solid-state batteries will be mass-produced in the next 5 years. Even though I also see, also with the semi-solid technology, the high potential from the functional point of view. So, one-sentence question to you. Do you see them coming or further ahead? Abdellah.
we are still far from commercialization at scale.
Okay.
And the issue is there has been massive investments in gigafactories that can produce NMC and LFP pretty well. And now we have to find the investments to do new manufacturing facilities for solid state. So it's not that solid state is not working, it's how do we produce it, manufacture it with the requirements on safety and control and quality at scale.
Okay, thank you for the assessment, and that was on the performance side. All right, so we have an all-solid-state battery, very safe, very high energy density in terms of gravimetric, but also specific energy, but also volumetric energy density, which is important for all applications beyond e-mobility even. So Kenza, you are already mentioning another technology, right? And that is sodium. So well, we have like this high-performance all-solid-state battery technology on the one end of the spectrum. We have the cost-competitive technology on the other end of the spectrum, and that is sodium-ion batteries. For all of you to remember, sodium is the salt that we sprinkle over our daily meals, right? So it's a very cheap component, a very cheap element, and a very cheap battery technology as such. So while we won't have the same energy performance as the high NMC and potentially semi-solid or all-solid-state batteries, we have a significant cost advantage on that side of the spectrum. But the question here is, the LFP technology has also become very, very cheap by now. Last year, the lithium prices were very high, like many, many percentage higher than they are this year again. So that was the reason why many companies opted in the research on sodium-ion batteries. This year, we see the lithium prices decrease again, raising the competitive burden for sodium-ion batteries again. So the question here is, will sodium-ion batteries, because they are so cheap but not that high of performance in terms of energy density, have a competitive advantage still? And where do you see the potential on the future outlook from the research perspective, Kenza?
Well, back to LFP materials. LFP is mature technology comparing to sodium-ion batteries, but it's what I can compare both, and I can tell you where we can find, in my point of view as scientist, how we can find for both technologies a market. For LFP, as I mentioned, is mature technology and it's very known by also the stability, thermal stability. We know before the LFP used to be for stationary application. Recently, there are LFPs in EV cars. Recently, CTL, they announced that... So
a big Chinese battery manufacturer?
Company, they announced that they could, just by changing the structure of LFP, means the material structure of the LFP materials, they could increase the energy density by 27%, which is very huge. And also they could lighter the weight of the pack, which is very important for EV application. They also mentioned that they can charge this battery fully charged at 15 minutes, which is a really big innovation for EV application. I can see that LFP will continue competing with all different technologies in coming even 10 years, not 5 years. But again, due to, don't forget that EV means the market for EV is increasing. We need a lot of batteries to be in the market. We cannot rely on only lithium-ion batteries because of the scarcity of these materials, which is cobalt, nickel, and lithium. That's why we need alternative. And this point where it comes the sodium-ion batteries, of course, as you mentioned, the energy density of sodium, it's not competitive with the energy density of lithium-ion battery, and this is very known. But also you mentioned that it's abundant. Sodium is abundant. All the sodium-ion batteries is made from cheaper materials, which will make this technology cheaper comparing to to the lithium-ion batteries,
I understand.
we can use this. This technology can be alternative in stationary, where we don't think a lot about the size of the battery packs, but the most important for us is the price for the stationary.
So what we need to underline here is that it's not just a technological issue on choosing the technology, but also a supply chain point.
Yes.
And also, and that is my final question to you, Abdellah, from the customer perspective and the market adoption, the performance point on sodium, do you see, also in terms of high power charging, Kenza just mentioned you can charge with LFP within a couple of minutes. Sodium will probably not be as fast. So you have the market experience. Will customers accept the lower performance in the future, which would create a market for sodium-ion batteries? Or would you say, no, it will probably be LFP still because of the performance advantage there? So because we are running a little bit out of time, maybe let's keep it focused, but of course I would like to have your assessment there.
Okay, so when you mean customer, you mean an EV driver or you mean the automaker?
Actually, I mean both, because in the first place, the automaker has to make its decision, but he makes the decision in consideration of his customer.
So let me be direct. I totally agree with Dr. Kenza.
Okay.
Here, I mean, LFP, there are still quite a bit of improvement.
Yes.
Yes, and improvement on the weight and improvement on the performance, and that's the cost of performance.
Yes.
Now, you didn't ask me the question about the anode, but if you pair this LFP with silicon anode, which is what Aqualith first generation product, and I love your fire there because we also have a second generation, which is a non-flammable electrolyte.
Okay.
But just with silicon, we can today, we've shown in the lab, we are demonstrating on pouch cells, and we are about to validate with OEMs. If there are any in the present, come talk to me. We essentially, comparing to a current Tesla Model 3 standard range, which very few people know uses LFP for the cathode and graphite for the anode. We can improve the performance with LFP and our silicon anode by 10% while decreasing the cost by 15%. All this, and that's the most important point, with just a drop-in current manufacturing. That means no need to reinvest into new gigafactories. We can scale this up once it's validated at the cell and pack levels for the various conditions for automotive. There you go.
Okay, then I have an understanding. So to summarize this discussion on the last point, making the point here that it's not solely about the technology. You mentioned also the industrialization point of view, not having to reinvent factories, which would take time, because to come back to my initial point, we need to be fast, right? And we need to take the options that are available now. And I think that really nicely summarizes the outline of the underlying message that, yeah, let's be fast, let's collaborate, and maybe, if I may, immobilize for the better. So thank you, everyone. Let's collaborate, have the dialogue on this forum here, and accelerate e-mobility. Thank you.